Hello viewers, today in this program I will explain you about the vector calculus. It is very old branch of the mathematics. The modern vector calculus have been developed in 19th century. Its introduction as follows. The vector calculus is a branch of mathematics concerned with differentiation and integration of vectors in two or more dimensions. It is very useful for physics and engineering, especially in the description of electromagnetic fields, gravitational fields and fluid flow theory. The vector calculus was originally introduced in the days of Aristotle 384 BC to 322 BC. In the last decade of 19th century, modern vector calculus was developed. Now I will explain you how we differentiate the vector. The vector differentiation is as follows. The vector differentiation is an extension of the concept of basic differentiation. When the vector is function of single variable, ordinary derivative is defined and partial derivative are defined when it is a function of two or more variable, as in the case of simple function of two or more variable. Ordinary derivative of vector is defined as follows. Let R be a vector which depends on the variable t. R is a function of t. If R is a function of t, is represented by OP and R t plus delta t by OQ as two vectors, then del R is equal to PQ, that is equal to OQ minus OP using vector rule, that is equal to R t plus delta t minus RT. The derivative of vector RT with respect to the scalar t del R over dt is defined as dr over dt is equal to limit delta t tend to 0 del R over del t, that is equal to limit del t tend to 0 R t plus delta t minus RT upon delta t, that is rate of change of R with respect to t when the limit exists. The general rule of vector differentiation is similar to the rules of the simple differentiation, and these are as follows. If a and b are differentiable vector function of a scalar variable t and phi is a differentiable scalar function of t, then the following identity holds true. The first identity is d over dt of a plus b is same as dA over dt plus dB over dt, that is called linearity property. Second one is d over dt multiplied by scalar function phi and vector function a, that is equal to phi dA over dt plus d phi over dt a. The third property is d over dt a dot b, that is dot product of two vectors, that is equal to a dot dB upon dt plus dA upon dt dot b. Similarly, the d over dt of cross product of a and b is given by d over dt a cross b is equal to a cross dB over dt plus dA over dt cross b. If a vector RT is a function of a scalar t, dr over dt, if it exists, is also a vector and a function of t. So, the derivative of a vector is a vector. If a vector r x, y, z and so on is a function of more than one scalar variable, then partial derivative of r is defined as del R over del x is equal to limit delta x tend to 0 R x plus delta x comma y comma z dash 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 minus r x y z dash 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 over del z, provided the limit exists. Here we have defined the partial derivatives in which x is the variable changes, y, z and other variables are treated as constant. This is the example representing the total derivative of r. It is the function of single variable. If r is a function of t as defined as t cube I plus t square j plus 4tk, then dr over dt is 3t square I plus 2tj plus 4k. So, the vector have after derivative again a vector, and if r is equal to x cube y I plus 3 x y square j minus 4 y 4 k, then del r over del x, here we are differentiating partially with respect to x and y, del r over del x is equal to 3 x square y I plus 3 y square j, keeping y constant. Similarly, del r over del y is equal to x cube I plus 6 x y j minus 24 y cube k. Here we keep y as variable and x as constant. Now, I will define partial derivative of vectors. If r is a vector that depends upon more than one scalar variable, say x, y and z, that is r is a function of x, y, z, then the partial derivative of r with respect to x defined as del r over del x is equal to limit delta x tend to 0 r x plus delta x comma y comma z minus r x comma y comma z divided by del x, provided the limit exists. This is the differentiation obtained when y and z keep as constant, and it is differentiation with respect to x variable only. Similarly, the partial derivative of r with respect to y and z are defined as del r over del y is equal to limit del y tend to 0 r x comma y plus delta y comma z minus r x comma y comma z upon del y. Here the y is the variable changes, x and z kept constant. Similarly, del r over del z is equal to limit delta z tend to 0 r x comma y comma z plus delta z minus r x comma y comma z divided by delta z. Here the differentiating with respect to z, so z is the variable changes, x and y kept constant. Example showing the partial derivatives as follows. The vector r is defined as x square y z I plus twice x y z j plus y z square k, that is a vector function of 3 variable x, y and z. Then we have partial derivative of r with respect to x, y and z are as follows. Del r over del x is equal to 2 x y z I plus 2 y z j. Similarly, del r over del y is equal to x square z I plus twice x z j plus z square k. Similarly, del r over del z is equal to x square y I plus twice x y j plus twice y z k. The higher order derivative of a function r x y z are defined as follows. The second order derivative of r with respect to x, second order derivative of r with respect to y, then second order derivative of r with respect to z. Similarly, the second order derivative of r with respect to x and y, with respect to y and z, and with respect to x and z are defined as follows. Now I will explain you the point functions in case of vector calculus. The point function is function whose value depend on the coordinate of a point in some specified region. For a point function, the dependent variable represents the coordinate of the point. It may be a scalar or vector point function. Consider a region in three-dimensional space. If for every point of the region there correspond a definite number defined by phi, then it is a scalar point function. It is also called a scalar function of position vector. In three-dimensional Cartesian coordinate x, y, z, it is any point, then the value phi x, y, z is also dependent on the time t. If it is independent of the time, then it is called stationary scalar field. For example, the density of solid, temperature of the earth surface is not a steady state scalar field. It is the temperature changes significantly at different time. Now, the vector point function consider a region in three-dimensional space. To every point of the region there correspond a definite vector v. It is called vector point function. A vector point function v may also be dependent of time or independent of time. Now I will explain you a very important vector operator, vector differential operator named as del operator and symbolized as del. A vector differentiation operator is defined as del is equal to I del over del x plus j del over del y plus k del over del z. It is the sum of three partial derivatives with respect to x, y and z in the direction of x, y and z coordinate axis. This operator is used to express some entities in vector calculus. Now I will explain you the entity of the vector calculus named as gradient. In vector calculus, the gradient is a scalar field described an important property of the field. It defined a vector field such that at any point it indicate the direction of the greatest rate of change of scalar field. Suppose phi defined a scalar field in some differentiable region, then the gradient of phi is defined as del phi, that is equal to I del over del x plus j del over del y plus k del over del z operated on phi, that is equal to del phi over del x I plus del phi over del y j plus del phi over del z k, that is sum of the partial derivatives of phi with respect to x, y and z in the direction of x, y and z axis. The example showing the gradient here is phi is equal to 3x square yz cube plus 5xy, a scalar function defined as, then its gradient is defined as grade phi is equal to 6xy z cube plus 5y, that is the partial derivative of phi with respect to x multiplied by I cap. Similarly, plus 3x square z cube plus 5x multiplied by j plus 9x square yz square multiplied by k, that is the gradient of the scalar function phi. I will explain now the physical interpretation of the gradient. Suppose phi xyz is equal to c represents a surface in space and p xyz be any point in a region, and let q x plus delta x, y plus delta y, z plus delta z is a neighboring point, then del phi dot del r, this is equal to del phi over del x I del phi over del yj plus del phi over del zk dot del xi del yj plus del zk, that is equal to del phi over del x plus del phi over del y plus del phi over del z, that is equal to del phi. It represents the change in phi. If P and Q lies on same level surface, then del phi is equal to 0, and therefore del phi dot del r is equal to 0. This implies that del phi is perpendicular to del r. Thus, del phi is normal vector to the surface. Now, I will explain you the second identity of the vector calculus, that is divergence. Let f is equal to f1i plus f2j plus f3k be a vector point function defined and differentiable at every point x, y, z in some region of space. Then the divergence of f is defined as the dot product of del operator and f, the given function. It is defined as del dot f is equal to I del over del x plus j del over del y plus k del over del z dot product with f1i plus f2j plus f3k. It gives you del f1 over del x plus del f2 over del y plus del f3 over del z, that is partial derivative of f1 with respect to x and partial derivative of f2 with respect to y and f3 with respect to z. It becomes the scalar. Now, I will explain you the physical interpretation of the divergence. Suppose a fluid moves such that its velocity at any general point P x y z is defined by V x y z is equal to V x x y z I plus V y x y z j plus V z x y z k, that is in the direction of x it is V x, in the direction of y it is V y, and in the direction of z it is V z. A vector point function is defined in the following figure. X component of the velocity v at p is Vx, then x component of velocity at the center of the phase ABCD is approximately Vx minus half del Vx over Vx multiplied by del x. X component of velocity of the center of the phase FGHE is approximately Vx plus half del Vx over Vx multiplied by del x. Therefore, the area of each of the face ABCD and FGHE is del y del z. Hence, the volume of the fluid entering the parallelepiped through the face ABCD per unit time is Vx minus half del V over del x multiplied by del y del z, and the volume of the fluid leaving the parallelepiped through the face FGHE per unit time is Vx plus half del Vx over del x multiplied by del x whole multiplied by del y del z. Therefore, the net decrease of the amount of fluid due to the flow in x direction is approximately del Vx over del x del y del z. Also, the effect of y and z components of the flow, the total volume decrease of the amount of fluid inside the parallelepiped per unit time is given by del Vx upon del x plus del Vy over del y plus del Vz over del z multiplied by del x del y del z, that is equal to del Vx over del x plus del Vy over del y plus del Vz over del z is equal to del dot V, that is equal to divergence of V. Hence, divergence of V gives the rate at which the fluid is originating at a point per unit volume. The example showing the divergence of a vector point function is as follows. If f is a vector point function defined by 6xyz cube plus 5yi plus 3x square z cube plus 5xj plus 9x square yz square k, then its divergence is defined as del dot f is equal to del over del x of this function f1 plus del over del y of function f2 plus del over del z of function f3, and we find finally 6yz multiplied by 3x square plus z square. An important deduction of the divergence of the function is as follows. If phi and psi are differentiable scalar field, then show that del phi cross del psi is solenoidal. The solution of this deduction is as follows. It is required to show that the divergence of del phi cross del psi is 0. Divergence of del phi cross del psi is defined as del dot del phi cross del psi, that is equal to del dot the determinant value of ijk del phi over del x, del phi over del y, del phi over del z, and in the third row del psi over del x, del psi over del y, del psi over del z, that is equal to I del over del x plus j del over del y plus k del over del z dot some expression in I, j and k as follows. On simplification this, we find this is equal to 0. Hence, del phi cross del psi is solenoidal. Now, I will explain you third identity of the vector calculus named as curl. If f is a vector function f1i plus f2j plus f3k, a vector point function defined at each point x, y, z in some region R, then the curl of f is defined as del cross f, that is the cross product of del operator with a vector function f. It is equal to I del over del x plus j del over del y plus k del over del z cross product with f1i plus f2j plus f3k, which can be expressed in the form of determinant. It is equal to the determinant value of I j k del over del x del over del y del over del z, and in the third row f1 f2 f3, which is equal to this expression. Now, I will show you an example representing curl of a vector function. If a vector function is defined as x y z square I plus 3 x square z square j plus 2 x y z square k, then curl f is given by the determinant value I j k del over del x del over del y del over del z, and in the third row x y z square 3x square z square and 2x y z square, which gives again a vector value as defined. Now, I will explain you the physical interpretation of curl. Suppose a rigid body is rotating about a fixed axis through the origin. Let omega is equal to omega xi plus omega yj plus omega zk is angular velocity, then the velocity v is given by v is equal to omega cross r. where r is equal to xi plus yj plus zk vector. Here v is equal to determinant value I j k omega x omega y omega z, and in the third row x y z, that is equal to omega y z minus omega z y I plus omega z x minus omega x z j plus omega x y minus omega y x k. That therefore, the curl of v is equal to the determinant value I j k del over del x del over del y del over del z, and in the third row the component of v in towards x, y and z direction. It gives you equal to twice of omega. Therefore, the angular velocity of rotation of a rigid body rotating about fixed axis is equal to half the curl of the velocity. That is why curl is also called rotation. If curl v is equal to 0, then the vector field v represents irrotational motion. Now, I will define some second order operator identity of the vector operated on scalar function phi and vector point function f. If phi is a differentiable scalar point function and f is a differentiable vector point function, then grade phi and curl f are vector point function and divergence f is scalar point function as defined earlier. Hence, the following second order operator can be defined. These are the 5 second order differential operators as divergence gradient of phi, curl gradient of phi, gradient of divergence of f, divergence of curl of f, and curl of f. Today in this lecture, I have discussed an important concept of vector calculus, which is an important branch of mathematics. Firstly, ordinary vector differentiation and partial vector differentiation has been defined, and then identities have been discussed with example. Then scalar and vector point function are defined with its dependence on time has been discussed. Then an important vector operator del has been defined. Then the 3 vector identities gradient, divergence and curl of vector point function has been discussed with example, and these are interpreted physically. At last, second order vector identities are defined. Hope you all enjoy the lecture. Thanking you.